The demise of the universe. Sounds like a scene only talked about in science fiction novels. In our previous concept, the universe is eternal. However, the deeper scientists study the universe, the more they discover that the universe itself as a whole is bound to be affected by physical laws. Restricting physical laws allow the universe to have its own life cycle. It will be born, it will evolve, and it will also die. If you want to understand the birth of the universe, you can watch the video about the book, The First 3 Minutes, which describes the beginning of the universe in detail. Today let's discuss the book The Last 3 Minutes of the Universe, written by Paul Davies, a world-renowned physicist. He became so passionate about the universe because he was inspired by the book The First 3 Minutes when he was young. You could say that Paul Davies wanted to write a companion book to The First 3 Minutes. That's why we have The Last 3 Minutes of the Universe. 2 books, one at the end and one at the beginning, telling the story of the life of the universe. Scientists today have all kinds of tools to help them study the universe, whether it's a new theory or a new technique. Using these tools, scientists have discovered that the universe has an end. In fact, as early as the 19th century, nearly 200 years ago, scientists at that time, without the advanced concepts and tools of today, had already deduced that the universe must have an end with the help of only 2 thought experiments. Let's take a look at these 2 amazing thought experiments. The first thought experiment is called Olbers' paradox. In the 19th century, there was a German astronomer named Olbers. He asked a question that has plagued the astronomical community for years. Why is the sky black at night? At first glance, you might think, what kind of question is that? There's no sun in the night sky, just stars and the moon. And the stars and the moon aren't as bright as the sun, so they're black. But if you think about it a little deeper, you'll see that the problem is far from simple. Both the sun and most of the stars at night are actually stars. Let's assume that every star has the same brightness. The reason the other stars aren't as bright as the sun is because they're much farther away from us. A star that's twice as far from the Earth as the sun is from the Earth is only a quarter as bright as the sun. If it's 3 times as far away, it's only 1/9 as bright. You see, the decrease in brightness is proportional to the square of the distance. But suppose the universe is infinite and the stars are evenly distributed. We can draw an imaginary sphere around the Earth. If the radius of the sphere becomes twice as large as before, then the number of stars enclosed in that sphere will be 4 times as large as before. The increase in the number of stars is also proportional to the square of the distance. So as you get further away from Earth, the brightness of the star decreases, but the number of stars increases. This subtraction and addition actually cancel each other out. If the universe is infinite, then all those stars, no matter how far away they are, should shine on the Earth as if they were countless suns. How can the night be black? The only possible explanation is that the original hypothesis was wrong. The universe is not infinite, and neither are the stars. The universe we live in is vast, but it has boundaries and mass. The second thought experiment was proposed by the German physicist Hermann von Helmholtz, one of the greats in the history of physics. He formulated the well-known law of conservation of energy. Also, famous physicists such as Planck and Hertz were once doctoral students of von Helmholtz. Von Helmholtz, on the basis of the thought experiment we just talked about, did a thought experiment based on the second law of thermodynamics. He then predicted that the universe would end. What is the second law of thermodynamics? Simply put, it says that in a closed system, if there's no outside interference, heat will always flow from a higher temperature to a lower temperature. This process is irreversible. You may say, no, that's not true. When we turn on the air conditioner in the summer, cold air blows out. Isn't that heat transfer from the lower temperature to the higher temperature? Please note that this is because our house is not a closed system, and there are external forces that interfere. If you move the air conditioner from outside to inside the house, all doors and windows are sealed. Then it becomes a closed system. When you turn on the air conditioner, you're cooling the house and dissipating the heat at the same time. It's impossible to lower the temperature in the house. It's the same in the universe. The flow of heat is also unidirectional. We have a good example right in front of us, the sun. The sun constantly radiates heat in all directions. It never comes back to the sun. One day the energy of the sun will run out, and it becomes the same temperature as its surroundings. Later, some scientists even combine the second law of thermodynamics with the concept of time. Since the flow of heat is irreversible, the flow of time is also irreversible. Thus, some scientists propose that the direction pointed by the arrow of time is actually the direction of heat flow, as determined by the second law of thermodynamics. So how is it possible to deduce the future of the universe based on the second law of thermodynamics? Because according to the previous thought experiment, we've already established that the universe is a closed system. The space of the universe is limited. The number of stars is also limited. Therefore, no matter how big the universe is or how complicated the movement of the planets is, the second law of thermodynamics will always apply to the universe. Heat will continue to flow from high temperature to low temperature. Therefore, von Helmholtz concluded that sooner or later there will come a day when the temperature in every corner of the universe will be exactly the same. After that, there will be no significant physical activity in the universe. It is like a pool of very shallow water. There is no way it can flow, and there will be no waves. Scientists have invented a word to describe this stagnant universe, calling it heat silence. Heat as in heat, silence as in silence. Von Helmholtz believed that if the heat in the universe stopped flowing, the universe would fall silent. That's the end of the universe. However, more than 100 years have passed since Helmholtz's time. Today's scientists' understanding of the universe has changed dramatically. So, let's move on to the second question. What are today's scientists' conjectures about the end of the universe? The first is a continuation of the heat silence theory, and scientists have found even stronger support for it. This is the Big Bang theory. Scientists have discovered that today's universe was born from a Big Bang. The universe began to expand from a very dense point and then continued to grow. Today's scientists are studying the Big Bang more and more. Like the book we mentioned at the beginning, The First 3 Minutes. In this book, scientists have been able to describe exactly what happened to the universe. In the 3 minutes after the Big Bang, almost all of the laws that govern how the universe works today have their roots in the effects of the Big Bang. One of these effects is that the universe is still expanding. Scientists have determined from their observations that the distances between galaxies aren't fixed, but are getting farther and farther apart. If the universe continues to expand, not only will the future universe have the same temperature everywhere, but the larger the universe becomes, the lower that final temperature will be. It's going to be infinitely close to absolute zero, which is minus 273.15 degrees Celsius. The closer you get to that temperature, the less kinetic energy particles have, and the less active matter becomes. So the expansion of the universe would bring the universe back to silence faster. That's the first theory that scientists have today about the end of the universe. But as they've studied the universe more deeply, scientists have come up with a second theory about how the universe will die. Some scientists believe that the universe will not continue to expand indefinitely. Those scientists who believe that the universe will continue to expand are actually missing a key factor, and that is gravity. Scientists look at stars that are nearing the end of their lives, and they found that these stars exhibit an amazing phenomenon called the gravitational slingshot effect. When a star is nearing the end of its life, gravitationally, the star will slowly drift towards the center of the galaxy. As it drifts, it will encounter other stars. The two stars will be attracted to each other, and they'll form a kind of magical orbit. The author uses a very romantic expression here. They'll form a pair of stars locked in a gravitational embrace. And if a third star comes along at that point, for example, if these two stars meet another star that is drifting toward the center of the galaxy, or if these two stars have planets, the motion of the three stars will be completely different, because the pattern of interaction between the three celestial bodies is always changing in a complex way. The orbits of these three stars cannot even be calculated. The famous science fiction novel The Three-Body Problem has such a setting. Although scientists cannot always predict the orbits of the three stars, they can predict the end result of the process. One of the results is that the enormous energy gathered by the attraction of the three stars will be transferred to one of the stars. That star will be completely kicked out, just like a projectile shot out of a slingshot. This energy is extremely powerful. This star might even be thrown out of the galaxy. In the end, it will most likely be captured by a black hole. And those stars that are not thrown out of the galaxy will continue to slide toward the center of the galaxy and eventually merge into a giant black hole. Therefore, under the influence of the gravitational slingshot effect, the final destination of the star is likely to become part of a black hole. If there are more and more black holes in the universe, and they get bigger and bigger, then the gravitational slingshot effect will intensify, and more stars will fall toward those black holes, and that sets off an avalanche-like chain reaction. The end result is that the universe goes from expansion to contraction. It's like the Big Bang in reverse. The universe returns to a point of infinite density. Some scientists have taken this a step further and come up with even crazier ideas. And that is, could our universe be stuck in this infinite loop of expansion, then contraction, then expansion, then contraction? Is the beginning of our universe the point at which the Big Bang began? At the beginning of the Big Bang, did it contract from the previous universe? This model that combines expansion and contraction is called the cyclic model of the universe. Our universe is like a cycle of lifetimes. Each new cycle is like a rebirth from death. A new universe is born out of the death of the previous one. New systems and structures emerge. New and colorful worlds are explored. And then it contracts again until it's destroyed. It's a very difficult assumption to verify. Suppose the cyclical model of the universe is true. Everything left over from the last universe would have been destroyed as it contracted to a single point. There's no evidence of that in our universe today. However, if we assume that the cyclic model of the universe is true and keep thinking along those lines, we'll come to an even more startling conclusion, that the next cycle of the universe will take longer than the last. Scientists have discovered that the Big Bang left behind a huge amount of heat radiation, and the universe carries this heat radiation with it as it expands outward. This radiation is called the background radiation of the universe. As time goes by, the light radiation from stars accumulates. After billions of years, the accumulated light radiation in the universe is almost as much as the background radiation. This means that when the universe contracts again, the radiation energy spread throughout the universe is much greater than the radiation energy just after the Big Bang. You may ask, isn't the universe a closed system? Conservation of matter and conservation of energy. Where does the extra radiation come from? According to Einstein's equation E=mc², the excess thermal energy is provided by the matter contained in the universe. The energy is completely converted from matter to radiation. As a result, the universe goes from contraction to extinction. It looks like the process of the expansion of the universe is reversed, but it is actually very different. For the universe at that time may be the same size as the previous universe, but with less matter and more radiation. The gravitational force of radiation is very different from the gravitational force of matter, so the effect is also different. This excess radiation will cause the universe to collapse faster. If there is some kind of rebound, then the next universe will also expand faster. In other words, the energy of each Big Bang should be greater than the previous one. With the beginning of each new cycle, the universe will expand to a larger scale. So the cycle will gradually become larger, and the time will become longer and longer. In other words, if the universe really goes through several lives, then the time experienced in the next life will be longer than the previous life. What is the ultimate end of the universe? We've talked about a lot of scenarios for the end of the universe. There's expansion, there's contraction, and there's expansion followed by contraction, which raises a new question. How do scientists determine which is the most plausible? What's the ultimate demise of the universe? Let's imagine the very distant future. What will the universe look like in 100 trillion years? At that time, most of the stars in the universe will have burned out. The universe is already dark, but it is not empty. There are countless black holes, neutron stars, and black dwarfs. However, the density of celestial bodies in the universe is very low. because the universe will expand to 100 trillion times its current size. As the universe expands, gravity will engage in a tug-of-war. The expanding universe is trying to pull each celestial body away, but the gravity between the celestial bodies is trying to pull them together. It's like a game of tug-of-war. So which side will win? That depends on the density of matter in the universe. The lower the density of matter, the stronger the force of expansion. The higher the density of matter, the stronger the force of aggregation. We all know that density is mass divided by volume. Today, scientists have been able to estimate the size of the universe by figuring out how big it really is. The next key to determining the fate of the universe is its mass. How do you weigh the mass of the universe? This seems like a daunting task. We can't weigh the universe star by star. We can't find a big scale to put the universe on and weigh it all. But scientists have found a way to think about it. They think they can use the theory of gravity to derive a result. The results may not be as precise as they could be, but it could help scientists calculate the lower limit of mass. How do we do this? We can measure the sun's gravitational pull on the planets and weigh the sun's mass. Scientists already know that there are about 100 billion stars in our galaxy. If we assume that the mass of each star is equal to the mass of the sun, we get the lower limit of the mass of the Milky Way. We can also calculate how many galaxies there are in the universe. The current reasonable estimate is 10 billion. Therefore, the total mass of the universe is 10 to the 21st power of the sun. This is the lower limit of the mass of the universe. In other words, the universe should not be lighter than this weight. If we assume that the mass of the universe is this much, what is the conclusion? Scientists have done some calculations and found that it's not very dense. If the universe only had that much mass, then we'd be in a universe that expands and expands and eventually goes into a heat death. Of course, that's based on the lower limit of the universe's mass. And that lower limit comes from the stars that we can see. But many scientists believe that the cosmic matter we see is much less than the cosmic matter that's actually out there. For example, there are many objects in the universe that don't emit light, such as dark stars and planets and black holes. So what is their mass? Is there dark matter and dark mass in the universe? And do some of the most massive but tiny particles, such as neutrinos, have any mass at all? Today's scientists have no way of answering these questions. Perhaps only after these questions are answered can we accurately calculate the mass of the universe. There is also a group of scientists who have taken a different approach. They have described another cosmic model. Their reasoning is that when you scientists think about the future of the universe, you think of the universe as a huge solid block. When it expands everywhere. And when it contracts everywhere. But you should pay attention to the fact that the density distribution in the universe is extremely uneven. So is it possible that our universe can actually be divided into small pieces? Because each piece has a different density, its changes are actually different. Just like soap bubbles. Some bubbles expand wildly. Some bubbles do not grow or shrink. And some bubbles have begun to shrink. This theory is called the cosmic bubble model, and was proposed by Russian physicist Andrei Linde. He even has other conjectures about the birth of the universe, that the universe didn't come from a single point. It could have just been a lot of bubbles. The bubbles that expanded the fastest took up the most space in the universe for a short period of time. Where we are now is just one of those highly expanding cosmic bubbles. Inside our bubble, matter and energy are almost equally distributed. But beyond our bubble there are others. On this larger cosmic scale, the universe still looks very chaotic. If Andrei Linde's predictions are true, then the end of the universe would be a very different picture. Because in Linde's model, the expansion never stops, even if some cosmic bubbles shrink. But there's always a new one forming. New cosmic bubbles will begin to expand and take over the space of the shrinking bubbles. This is another form of the eternal universe, even crazier than the cyclic model we just talked about. If the cosmic cycle model is like a person's birth, aging, illness, and death over several lifetimes, then this cosmic bubble model is already countless people, competing with each other according to the law of the jungle. The universe is like a throne. The bubbles are like rivals. there's always a strong young man who can knock the old king off the throne and replace him. In such a universe, life, hope, and the universe are eternal. Each bubble can live and die, but the whole universe in this game of grabbing chairs lives on. Of course, with today's science and technology, whether it's heat silence or contraction, the cyclic model of the universe or the bubble model of the universe, they are all just guesses by scientists. At this point, it's impossible to predict the future of the universe. We can only hope that in the future scientists will be able to better understand the universe. Then we'll have a clearer picture of the future of the universe. And finally, I'd like to share with you an idea I read in a book. We've talked about many ways the universe could end. Then the author asked, is there anything we humans can do? Can we do anything to slow down the end of the universe? At first glance, there's nothing we can do. No matter how powerful we are, we can't compete with the laws of physics. On the scale of the universe, we're no different than ants. But the book offers another way of thinking about it. We may not be able to slow the decline of the universe, but we can find a way to transform ourselves, to increase the speed at which we process information, and to increase the speed of our metabolism. Because for humans, time is a relative concept. If our minds and bodies are fast enough, then a few minutes can be years. In principle, if we can master the method, we can increase the speed of information processing and metabolism. Then the remaining time in the human brain can be extended indefinitely. With this kind of technology, even if the universe is only 3 minutes away from extinction, we could experience thousands of years of time in those 3 minutes. Human beings could live almost forever. I think if this technology can be realized, the last 3 minutes of the universe will not be so frightening. For human beings, the last 3 minutes of the universe will be less scary and less bleak. Okay, that's it for this video. If you like our video, please like, subscribe, and forward it to your friends. Feel free to share your thoughts in the comments section. See you in the next episode.